Okay. Hello, everybody. Hope you guys are having a good week so far. Getting adjusted in the online class. So I am going to start this video in section 2.1. And just so you guys know, if you're going straight to the textbook for chapter 2, they are kind of like a section behind. So they're not aligned with the Pearson assignments. But if you're going into Pearson and then going to assignments and clicking on the e-text and video assignments before each section, then it'll bring you to where you need to be. So I think like for 2.1, it actually brings you to 2.2. So just be aware of that, but these notes here and will align with the Pearson assignments. Also, in case y'all haven't noticed or you didn't see my description about this, but all of my notes are posted under files and Canvas as well, if you need to access those. Okay, so this first section, 2.1, is all about beginning to analyze the different properties of functions. And so I just included this library of functions here just so you can have it. But, you know, we're going to be doing more with the library of functions, I think, in section 2.5 when we are talking about transformations of functions. But I wanted to go ahead and introduce you to these so that you know, have seen them and you get familiar with them. So the first one, these are just basic functions of particular types of functions. So we've been learning in chapter 1 about linear functions. So this first function here is the identity function, which is the most basic function for linear functions. And that is the equation y equals x. The next one is the squaring function, which is y equals x squared. So this is the most basic equation for a quadratic function where the vertex is at the origin 0, 0. And it makes this U-shaped. And then the next one is the square root function, which is y equals the square root of x. And so if you've kind of noticed, we cannot take the square root of a negative number. So when we talk about the domain of this function, we're talking about all x values that are 0 or positive. So that's why you see this function get cut off there at 0. There's no negative values for that function because I can't plug in -1, -2, or anything negative. And so actually the domain of this function would be from 0 because it can equal 0 with a bracket, and then it goes off to infinity. And the range, which is the y values, is also the same because the first y value you see looking from the bottom up is that 0 there. So that range for that function is also from 0 with a bracket to infinity. Then the next function is the cubing function. So this is y equals x cubed. And this is the basic shape of a cubic function where it has like two little curves and it goes through the origin. So if we're asked about the domain of this function, this is going to be from -infinity to infinity because this function goes off forever to the right. So it's going to keep going forever up and kind of tilting to the right. So if I pick like 100 for x over here, there will be a point up here associated with 100. So it keeps going forever to the right. So that's why the domain goes to positive infinity. Same thing for negative infinity because it's going forever in the bottom direction here. And the range will also be -infinity to infinity for that as well. And then the last three are the a little, you know, less common. You won't see too much of this cube root function in this class, but we will be talking about rational functions a little bit later on. And so this is the most basic equation for the rational function, which is called the reciprocal function. And that's y equals 1 over x. And just remember the restriction on functions that have fractions is we cannot divide by 0. So in this function, x cannot equal 0, but it can equal every other number. So the domain would be all numbers except for 0. And then the last one is the absolute value function. So I don't want to spend a whole lot more time on that. We are going to talk more in depth about each of these types of functions a little later on in the course. But I kind of just wanted to introduce you to them now, since we're going to be analyzing properties of functions in this section. So these are the different types of properties that we're going to focus on in this 2.1 section. The first one is domain and range, which I kind of just touched on a little bit on those functions. The next one is finding the zeros or the x-intercepts, and then the y-intercepts. And then we are also going to be finding the intervals for which a function is increasing, decreasing, or constant. And then finally, we're going to be finding the maximum and minimum values of functions. So for a zero, finding the zero of a function, by definition, an input for a function, so an x value c, is called a zero if the output for the function is 0 when you plug c in. So when we plug a value into a function and we get 0 as an output, then that x value that we plugged in is called a 0. And therefore, we just found the point c comma 0, because x was our input and 0 was our output. And this is the same thing as an x-intercept, where the point crosses the x-axis. So this first example says to use a graphing calculator to find the zero of the function. So first, I'm going to show you how to do this by hand without using the graphing calculator. So anytime they ask you to find the zero of a function, you're just going to set the entire function equal to 0. So I would have 0 is equal to x squared minus 5x plus 6. And this is a quadratic equation. And we can factor this by finding two numbers that multiply to give us 6 and add to give us negative 5. And I'm going to be doing more of an in-depth review of factoring next week, I believe, or maybe 2 weeks. So don't worry too much. I'm going to show you how to do this on your calculator as well. But this will factor, or the two numbers that multiply to give us negative 6 and add up to give us negative 5 are negative 3 and negative 2. So this will factor to x minus 3 times x minus 2. And then we set both of these factors equal to 0 and solve, so we get that x is equal to 3 and x is equal to 2. So these are our two zeros of this function. But now I'm going to show you how to do this using your graphing calculator. So hopefully you all have your graphing calculator by now, because you will need it for your exam. So once you're on your graphing calculator here, to enter a function, you're going to go to y equals, which is that top right button, highlighted in red. And then to do a variable, you click on that x t theta button that's highlighted in red there. You can do an exponent by clicking on that up caret arrow and then typing in 2. And then you'll have to get out of the exponent by doing the right arrow button. And then it was minus 5x plus 6. So I entered that function in, and now I'm going to hit graph. And the graph will look like this. And we want to find the x-intercept and the y-intercept, or I'm sorry, the two x-intercepts, because we're trying to find the zeros. So when they ask you to find the zero of a function and you use your graphing calculator, you need to know that it is an x-intercept. And in this function, there's 2. It crosses the x-axis in 2 places. So to do this, to figure out the actual value of those 2, I'm going to do second, the blue button at the top, trace or calculate to get to the calculate. And then we're going to go down to 0, which is number 2. And then you hit enter. And it brings this little cursor, which you can move around using the arrows. And I want to bring it around the left of the first x-intercept because it says left bound question mark at the bottom of the screen. Once I get it to the left, I hit enter. And now it says right bound question mark, so I want to bring it to the right, which is a little below. Hit enter again. And it gives me the 0 of 2 right there, which is one of the answers we found by hand. So that's great. And now I can do the next one by starting over, hitting second, calculate again, going down to 0, hit enter, move it over to the next x-intercept, and it wants a left bound, so that would be a little below. Hit enter. Then it says right bound, so I'll go a little bit above and hit enter. And hit enter one more time. And it gives me the answer of x equals 3. So that is how we can find the 0 of a function using our graphing calculator. And you can also find the y-intercept of this function, which is where it crosses the y-axis right here. I'm trying to get my cursor there, right there. By doing the same button, second, calculate, and then you can go to value and hit enter. And the y-intercept is whenever x is equal to 0. So we want to put 0 there for where it's asking us to enter a value for 0. Hit enter. And that value is 6. So the y-intercept of that function is 6. Okay. The next example wants us to find the 0 of the function f of x is equal to 3x plus 8. So for this, it's a little bit easier just to set this equal to 0 and then solve for x. So the first thing I would do is subtract 8 to both sides. And then divide both sides by 3 to get the x by itself. So x would be equal to -8/3. And this would be the answer. That is the 0, because I set that function equal to 0 and then I solved for x. All right, the next thing we're going to talk about is how to find intervals of increasing, decreasing, or constant intervals on a function. So this is the mathematical, technical definition, and I'm going to go over that first and then kind of tell you an easy way to figure it out. So first it says a function f is said to be increasing on an open interval. So this is important. We always want these answers of our intervals to be open, so with parentheses. An open interval I, for all a and b in that interval, if a is less than b, and here we're talking about the x values, so in this picture down here, a is less than b, because it comes before b on the x-axis, implies that the output of a, which is here, the y value, is less than the output of b, which is here. So that is the definition of it when a function is increasing. And you can also see that if I put a little stick figure on here, a little stick man, and I tell him to walk from left to right, he'd be walking uphill. He's walking uphill. So that's another way you can determine whether it's increasing or decreasing, whether he's walking uphill from left to right or downhill. Then the next one is similar definition. Function is decreasing on an open interval I if the x value a is less than b, but the output of a is greater than the output of b. So here we see that this output is greater than this, it's higher. And again, if I put a stick figure guy up here on my function all the way to the left and tell him to walk from left to right, he'd be walking downhill. Okay. And then of course a function is constant if it's just like a flat horizontal line. Now the interval for which this is increasing or decreasing over is equal to the interval of x values where this is occurring. So for this function, it's starting here, whatever x value this would be, and it's ending here. So the interval would be the interval of the x values of where over which that occurs. So it's always the x values. So let's look at an example. This says determine the intervals for which the function below is increasing, decreasing, or constant. So if I look at this function from left to right, if I start all the way to the left, I'd be starting here, and that's going down forever because of that arrow. And if I move from left to right, I'd be moving up, and I'd be moving up until right there at the top of that hill. And then after that, I would start to be moving down. So what's highlighted in blue is increasing, and what's highlighted in green is decreasing. And then the last one, at the bottom of that valley there, it would start to, I would start walking back up again. So that would also be increasing there. So for the intervals, let's start with the intervals of increasing. And remember, this is over the x values. I'm going to do my intervals from least to greatest, just like all intervals should be, over the x values. So for this first blue one, it's going forever and ever this direction. So it would start at negative infinity and then stop at the x value of 0 here. And then the next interval for increasing, which again, let me highlight this in blue, increasing intervals, starts at the x value of 2 right here. And then it goes off to positive infinity. And with these, you can separate your answers using a comma. It'll tell you to do that in Pearson. And just remember, I used open intervals for these increasing and decreasing intervals always. So now we will find the interval for which the function is decreasing. And that is the section of the graph in green, highlighted in green. So right here, this starts at the x value of 0. And then it goes to the x value of 2. So that's the only interval for which it's decreasing. Okay. And let me rewrite this because it's a little wonky there. All right, next example. Same thing, we're finding the increasing, decreasing, or constant intervals. So for this example, our function is not going forever in the right or left because we don't have the right arrows. We have closed circles or open circles. So just be careful of that. But still, when we talk about the increasing, decreasing intervals, it'll still be open intervals, so parentheses always. So for this one down here, let's start with this one down here. This one is constant because it's a flat horizontal line. And that interval starts at the x value of -6 right there. And it ends at -5. And again, both would have a parentheses. And then we'll move on to the increasing intervals. And the first one here would be this next piece of that line that's going uphill. And then there's another one over here that's going uphill. So for that first one, the first x value starts at -5 and it goes to -4. And then the next interval starts at -2 right here. And goes to +6. So that's the interval that I am working on now. So that's for the increasing, and then finally the only piece that's decreasing is this little piece here. And that would be from the x value of -3 to -2. Okay. All right. Next thing we're going to do is learn how to find the relative maximum and minimum values of a function. So there is such thing as a absolute maximum and absolute minimum, but we're not going to be learning that right now at this moment. But the relative max and min values, which is also sometimes called the local maximum and local minimum, same thing. I like local better because it kind of reminds me it's like in the neighborhood. So when we're finding relative maximum or relative minimum values, we're not going to be looking at the endpoints at all. We're only talking about what's happening in between the endpoints. So even if those weren't arrows, wouldn't matter. So for the local maximum, these are going to be any values, any y values that are at the top of these hills that you see. So like this one right here, it's pointing to, that is at the top of that hill or that peak. So whatever y value that is, whatever value that lines up with f of c of 2, that would be our local maximum. And then for the local minimum value, these are going to be at like the bottom of these valleys here. And it's just more technical what this definition up here says is it's the y value that is smaller than any other y values in an interval of an open interval. So this value here is smaller than any of the values in an interval that I could, if I choose this to be my interval, local interval. But it'll just be any of the points at the bottom of the valleys is how I like to explain it. So this one has 2. You see the 2 in green. That's your local minimum. And remember, these are always going to be the y values. So this would be f of c of 3 and f of c of 1. That would be 2. So let's do this first example, which says find any relative maximum or minimum of the function pictured below. So for this graph, this is an upside down parabola. And so there's only going to be one relative maximum value because there is no valleys. There's only, oh, sorry, let me fix this. There's only the top of this hill right here, or this mountain peak. That's it. It's going to be the only relative maximum within this neighborhood of x values. If I cut this down to be my neighborhood. And so the relative maximum is equal to 800, the y value there. And then sometimes it'll say it occurs at, and that will be the x value. But the actual maximum value is the y value. And that's it. Okay. So number 2 says to use a graphing calculator to find the intervals for which the function is increasing, decreasing, or constant, and find any relative maximum or minimum values. Round your answer to the nearest hundredth. So here is this function, and I'm going to go to my graphing calculator and type this function in. So I'm going to go to y equals and clear that first function that I had there. And the function was 1/2 times x cubed. So I'm going to put my 1/2 in parentheses and type 1 divided by 2. And then x. Then use the up arrow to get to the exponent, type in 3. And then minus 2x plus 5. So that is our function. And I'm going to hit graph. And it looks like this. If yours doesn't look like this, you might need to zoom out or zoom in a little bit. And just remember, we are trying to find the maximum and the minimum values. So if I use this cursor, this point here where I have the cursor, this would be a local maximum because it's at the top of a hill. And then this one over here would be a local minimum. And I need to know those anyways to make my increasing, decreasing intervals. I need to know the x values there at least. So I'm going to have to find those points. And my function will be increasing from the left up until this point where that maximum value occurs. And then it'll be decreasing from that x value to the x value of this minimum, local minimum. And then it'll be increasing again from that x value to infinity. So to find these values, you're going to go back to your second trace button. And there's actually a minimum and a maximum there. We're going to find the maximum first. So you go down to maximum and you hit enter. And then it brings up the cursor and it's asking for a left bound again. So I want to go to the left of where I think that maximum value occurs, which is about right there, and hit enter. And then a right bound. So I'm going to go to the right of where I think that maximum value occurs and hit enter. And then it'll make me hit enter one more time to guess. And it gives me the x value of negative 1.1547. And the y value of 6.5396007. And we're going to round these to the nearest hundredth. So I'm just writing them down now, and I'll write them on our notes when we go back. So that's the point of that first, where that maximum value occurs. And now we're going to find the local minimum value. So we go second trace and go down to minimum, hit enter, and now the local minimum value is over here. So I'm going to do left bound and hit enter, and then go to the right bound and hit enter one more time. And that x value is 1.1547 and the y value is 3.46039. Okay. And this was my max. Or sorry, well, the one we just did was the min. I was talking about my notes. All right, so let me go back to here and I will draw a rough sketch of this graph. Okay, so right here was that point we found the x value, and I'm going to round that to the nearest hundredth, was negative 1.15, and the y value was 6.54. And then here for this minimum value, the x value was positive 1.15. So my drawing isn't to scale, but that's fine. And the y value is 3.46. So the local maximum value, which is the y value, is that 6.54, and it occurs at negative x equals negative 1.15. And then the local minimum is 3.46, and it occurs at x equals 1.15. So that's that answer. And then the intervals for increasing will be starting from here, negative infinity, going all the way up to there. So that first interval would be from negative infinity to negative 1.15, because remember we have to use the x values, and it's an open interval. And then the next one for increasing would start here at that bottom of that valley and then go up to infinity. So that would be at the x value positive 1.15 and then going to infinity. And then for decreasing, it would be this little piece in the middle here, which would start at the x value of negative 1.15 and go to positive 1.15. Okay. The next example is an example of a type of word problem they can give you and ask you to find the maximum of something. These are called, or they'll be asking you to maximize or minimize a certain function. In this one, we're going to be asked to maximize the area of an office space. And this says that a community college has 30 feet of dividers with which to set off a rectangular area for a student testing center. If a corner of the math lab is used for the testing center, the partition, which comes from the dividers, the 30 feet of dividers, need only form two sides of a rectangle. So for this problem, they'll actually provide a picture for you. I'm just going to draw it real quick. So this is the math lab, and they're saying that they're going to cut off a corner here using that 30 feet of dividers. So let me put this 30 feet of dividers. So they want this wall and this wall to add up to 30 feet. They're going to use all of it. And the first thing they want me to do is express the floor area of this testing center as a function of the length of the partition. So the length of the partition, that's what we don't know. So I'm going to let that be my unknown variable. So the length of the width here could be x, and then the length of the length would be 30 minus x, because that's what's left from the 30 feet of dividers. But again, they actually have this picture for you on this one. But you do need to know what the area formula of a rectangle is, which is length times width. And anytime you're asked to, down here it says, find the dimensions of the two walls that would give the maximum area. You'll always need to find the function that they're asking you to maximize, which they're asking me to find the maximum area. That's why they're kind of breaking this up in steps for me and wanting me to find the function for the area first. So in this case, the length is equal to 30 minus x, and the width is equal to just x. So the area, which would be a function of x, so I could write it like that, and our function notation would be the length, 30 minus x, times the width, which is x. And you could distribute that x, which would give me 30x minus x squared. And then they want me to graph this. So we could use our graphing calculator and then use the graph to find the x value, which is the width, that would give the maximum area, because the maximum area would be the largest y value that we're going to see on this graph. So let's go back. And type in 30x minus x squared and hit graph. And here it's going to be hard to see the parabola, so I'm going to zoom out quite a few times till I can see the top of the parabola, because that is the maximum value at the top of that blue, because I want the largest y value. So I'm going to go to second, calculate, go to maximum, hit enter, do my left bound, which could be right there, is fine, that's to the left, enter, and then right bound, so I can go to the right, should be there, is fine, hit enter, and the maximum value there is the y value, which is 225. And the x value that occurs at, I'm just going to round it to 15. So go back. Again, this is all the possible areas of this testing center given the value of x. But knowing that they both need to add up to 30 feet. So we just graphed that. And I'm just going to kind of graph this, whatever. But this was 225. So the largest area was 225 square feet. And then the x value, which is the width of this rectangle that occurred at, was 15. So that means that the width that gives the maximum area would be 15. And the length would be 30 minus 15, which would also be 15. So this would actually end up being a square. So sometimes they'll give you problems like that and you will have to find the function, and it might not be about the area, it might be about a volume of a box or different types of things. And so you'll just look, if you don't remember, you'll look up the formulas you need to build the function and then create the function and find the maximum value. Okay, and finally, the last thing in this section is regarding piecewise functions. And so some functions are defined piecewise using different output formulas for different parts of the domain. So for example, here is a piecewise function down here. So the first pieces here on the left, these are the output formulas that they described in that definition. And then to the right, this is telling you what the domain for each piece is. So for x plus 3, the domain is all values less than or equal to 1. And for 5 minus x, the domain is all values greater than 1. So these are only graphed in pieces. The first piece, which I'll label as 1, and then the second piece I'll label as 2. If we graph them, which we're going to do, it's only graphed for the values in the domain that's given. But before we graph it, we're going to find these values here that it's asking me. So remember, the first one, this is g of 1. This is notation to tell me to plug in 1 for x into this function g. But because this is a piecewise, I can only plug this into the piece that has 1 in its domain, which is piece number 1, because that is all values of x less than or equal to 1. So I can plug it into the first piece for x, so that would be x plus 3, or 1 plus 3, which is 4. So g of 1 would be equal to 4. And then the next one is g of negative 1. And there I would also have to plug it into the first one, because it's less than or equal to 1. Negative 1 is. So that would be negative 1 plus 3, which would be 2. And then finally, g of 8. This would have to be plugged into the second piece, because 8 is greater than 1. So I would plug it into 5 minus x, which would be 5 minus 8, which would be negative 3. And I also just found points on this graph. So this one was 1, 4, because I plugged 1 in for x and got 4 out. And then the next one is negative 1, 2, and then 8, negative 3. And then to graph the piecewise function, we can graph 1 and then we'll graph 2, the lines. So for the first one, you always want to start with the endpoint. So the endpoint's going to come from whatever is on the end of this inequality for the domain. So the first thing I would do is plug g of 1 in. But I already did that. I said the first thing I would do is plug 1 in to G. But I already did that up here, so I got 4 right there. So the first point I can plot is 1, 4. Should be right here, and it would be a closed circle because 1 was included in the domain there. And then because this is less than or equal to 1 for the first piece, I need to pick an x value that's less than or equal to 1 to find my second point. And I already did that. I plugged in -1, and I got 2. So this would be -1, 2. And then I connect these 2 points going in the left direction because I'm only graphing values less than or equal to 1 for that first piece. The second piece, again, I'm going to start with this value on the inequality to see what my graph is doing at that point. So I'm going to plug 1 into that piece, even though it's not in the domain. So 5 minus 1 equals 4. So that's the same point, 1, 4. Now this would technically be an open circle because it's not including 1. But because there's already a closed circle there, it would remain closed because it's closed for the other graph, for the other piece. So it's just going to remain closed right there. And then we need to find one more point, and I already found g of 8, so I'll use that. This was -3. So that would be 8, -3, which would be right here. So then I connect those 2 points. And that would be the graph. Okay, last one of this section, and I will try to have 2.2 posted today as well. This has 3 pieces, and most of these, they will have multiple choice for you on Pearson. So a lot of it is about a process of elimination. So the first thing I'm going to do is look at this constant, because this means that f of x is equal to -2, and this is a horizontal line. And it's only a horizontal line at -2 for x between 2 and -3. Because of this domain here. So I'm going to look on my graphs, and both of these endpoints for that horizontal line should be open circles because they are not including those endpoints of -3 and 2. So that is going to eliminate B and C, because if you see this horizontal line at -2, they have closed circles. So those are not it. So that, what am I thinking of the word? It's escaping me. By process of elimination, that only leaves us with A and D. So now we're going to look at the other 2 pieces. So for this piece, it says that the domain is less than or equal to -3. So everything to the left of -3. And this is a decreasing line because of the slope. The slope is equal to -1, so it's decreasing. So that even narrows it down to the final answer, which has to be D, because this line here is decreasing, and this line is not. So this is the correct answer. And you can even see if I plug -3 into that x value, that would give me a +3 minus 3, which is 0, which is what that point right there is. So that lines up. Okay, I'm going to stop there. That is the end of 2.1, and then hopefully I'll get 2.2 up for you by today as well.